All right, so let's try to develop the formula for this binomial distribution because it is so common. Suppose you're playing a game of chance that requires you to roll 2 fair die and observe if you get doubles. The game requires you to perform 5 consecutive rolls of the 4 dice. I think it's supposed to be 2 dice, right? You're going to perform 5 consecutive rolls of the 2 dice. You got 2 fair die. You want to see what the probability is you get doubles. Let x equal the number of doubles in the 5 rolls. So first of all, we need to kind of review how likely it is that you get doubles. And I don't really want to spend a whole lot of time on this, but if you remember this sample space, equally likely outcomes, there's 36 squares in here. And basically, these are the ones, that diagonal are the ones where you get doubles. So that's going to be 6 out of 36, which is 1/6. So the probability that you get doubles when rolling 2 fair die is 1 out of 6. Okay? So that's kind of what we need to set up this problem. So is x a binomial variable? If so, identify n and p. Well, let's check the bins real quick. Binary, either I get a double or I don't. Independent, if I get a double on one roll, it doesn't influence the second roll. Set number of trials, yes, I'm rolling it exactly 5 times, 5 consecutive rolls. And does the probability of success change on each attempt? No, the probability of success is always 1/6. And most importantly, are we recording the number of successes in 5 rolls? Yes. We are recording the number of successes, the number of doubles in 5 rolls. So binomials, no. We have a binomial model. Find the probability that x is equal to 0. So this is a probability that you get no doubles. Well, there's only one way to get no doubles. You have to not get a double on the first. That's 5 out of 6. You have to not get a double on the second. That's got to happen 5 times in a row. And I'm actually less curious about these actual numbers than I am the patterns here. But let's just calculate it. Parenthesis 5, 6 raised to the 5th power. 402. So the 40% chance that you're not going to get any doubles. Okay. Find the probability you're going to get exactly 1 double. Well, here's why this one is a little bit difficult. There's a lot of different ways to get 1 double in 5. You could get a double, no double, no double, no double, no double, no double. Or, by the way, these are little ands in here, right? A double and not a double and not a double. Or you can, I think I got too many ends there. 5 rolls, 1, 2, 3, 4, 5. Or you can not get a double and get a double and not and not and not. Or not, double, not. Or not, double, not. Or not, double. So basically there's 5 different ways to get 1 double in 5 rolls. So we have to add up all those different outcomes. This one is going to be, you get a double, which is 1/6, and then you get 4 non-doubles. And we have independence, so that's why I can use a multiplication rule like this. That's why we need independence up here. Or, plus, you could get a 5, 6, not, and then 3 more 5, 6. So basically, hopefully you guys can kind of see that in each of these cases, I'm going to get 1 double and 4 no doubles. These are all exactly the same. So that means I'm going to get 5 times my 1/6 to the 1 and my 5/6 to the 4. So just to point out where we're going with this, this is counting the number of different ways I can arrange 1 success in 5. This is counting the probability of a success to the 1 power, because I'm getting 1 success. And this is counting how many failures I'm going to get, 4 failures. Now let's do 2. So this would be the probability. Well, how many different ways can I get 2 successes in 5? Well, I could get a double, double, no double, no double, no double, or double, no double, double, no double, no double, or... So you're probably already thinking, well, man, I don't want to count up all these things because there's so many different ways you can do it. That's what the binomial model is going to help us with. So this is going to be, I don't know if I want to count them or not, but I guess I will. D, D, N, 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 D, N, D, N, N, D, N, N, D, N, D, N, 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 D. So that's all the ones that have D's first. Now let's do all the ones where D is second. Not a D, 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 N, 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 D, N, D, N, N, D, N, N, D. That's all the combinations, I gotta be careful with my words here now. This is gonna be related to your combinations and permutations that you've kind of seen before, but I don't want to get too heavy into that, but we'll talk a little bit about it. So let's do all the ones that start with 2 N's, and then a D, DN, NN, D, ND, N, 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 D, D. There, I think that's all the different ways you can do it. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to have 10 of these. And all of them are going to have 2 successes, a double and a double, and 3 failures. Not a double, not a double, not a double. So it's going to be different combinations of that, but it doesn't matter when I multiply. I'm going to have 10 of them that I'm going to add up. So that's going to be 10 times. Again, this is counting how many different ways I can order 2 successes in 5 trials. This is the probability of getting 2 successes in 5. And this is the probability of getting those 3 failures. So in general, that's the binomial model. The probability that x equals just any number is going to be the number of arrangements times the probability of a success to the number of successes times the probability of a failure. By the way, I'm going to call that Q. If the probability of a success is P, I'm going to call this Q. Probability of failure is going to be the number of fails. This is easy. This is easy. This is the thing that's kind of difficult to calculate. And again, I'm not going to go too much into this, but basically I have 2 successes and 5 different places that I can choose those successes. So the question is, how many different ways can I choose 2 spots out of 5? If you remember from your combinations and permutations stuff, I have 5 different possibilities and I need to choose 2 of them. It's the combination. How many different ways, let's call these orders 1, 2, 3, 4, or 5. How many different ways can I choose 2 positions out of those 5? Well, I could get a 1, 2, I could get a 1, 3, a 1, 4, a 1, 5. That's these. I could get a 2, 3, a 2, 4, a 2, 5. That's these. I could get a 3, 4, or a 3, 5. That's these. Or I could get a 4, 5. Those are the number of ways that you can choose 2 out of 5. That is a combination. That is the binomial coefficient. That is the number that's going to go out in front here that's going to count the number of orders. So here's the binomial coefficient. Don't worry if you don't remember combinations and permutations, all that stuff. You don't really need to know it. But this is what it is. It's n choose k. Binomial coefficient, also written like that. Combinations. It's calculated by taking n factorial divided by k factorial times n minus k factorial. And our calculators will do this. We'll go over that. So here's the binomial formula. If you have a binomial distribution with n trials, and p is the probability of success, then the probability of getting k successes is n choose k, the number of trials, divided by, or choose the number of successes, my binomial formula here. Then I have the probability of success to the k power, and the probability of a failure to the n minus k. After all, if n is equal to 10 and you're getting 2 successes, that means you're getting 10 minus 2, or 8 failures. So that's the binomial theorem, the binomial formula, and this is on your formula sheet. Okay? So I'm going to talk about calculator shortcuts and how to do this on the next video.